Volumes by cylindrical shells. Suppose we have the function y equals 2x squared minus x cubed on the interval from x equals 0 to x equals 2 and bounded below by the x-axis. So we have this area here. Now if we rotate that region about the y-axis, we will get a three-dimensional shape. And to find the volume using the method of washers, our previous method, we would need to draw a sample rectangle horizontally so that we could identify the inside radius and the outside radius, which I call little r and big R. But to do this, you would have to solve for x. So what that means is you have to take your original function and solve it for x. But how do we do this? Well, in this case, it is hard to do this. It's very difficult to solve for x here. There is a way to do it, but it's not something that is taught in more elementary math courses. So we want to try to see if there's a different way to approach this problem. What if we drew the rectangle this way instead of drawing it horizontally? How would that be different when we rotate that around the y-axis? So this brings up the method of cylindrical shells. So we're going to come back to this problem as our first example. But first, let's talk about the fundamentals of finding a volume using cylindrical shells. To use the method of cylindrical shells, we first need to explore how you would find the volume of a cylindrical shell. So what is a cylindrical shell? Well, you can see a picture of one here. So let's keep in mind that a cylinder is a shape that has a circle on the bottom of the shape, and it is uniform all the way up to the top. And we can talk about the surface area or the volume of a cylinder. But a shell is when you're not looking at the entire cylinder. You're just looking at the outer wall of the cylinder. So if I just look at a particular thickness all the way around, and we do that same thickness uniformly down to the bottom, this is going to create a cylindrical shell. So we only have material around the outer edge of the cylinder. But even though it's a very thin piece, it still has a volume. And so we want to try to figure out what is this volume. So first, let's remember the volume formula for a cylinder. So we should know that the volume is the area of the circle on the bottom, which is pi r squared, and then multiplied by the height. So how do we find the volume of just this shell right here? Well, notice that there are two radii here. We have the radius from the center to the outer edge. We're calling this R2. And we have the radius from the center to the inner edge, and we're calling that R1. And don't worry about what R is at the moment here. So to find the volume of the cylindrical shell, what I'm going to do is take the volume of the outside cylinder minus the volume of the inside cylinder. So the volume of the shell is going to be the volume of the outside, which is pi times R2 squared times h, minus the volume of the inside, which is pi times R1 squared times h. And now I'm just going to algebraically manipulate this expression. So notice that I can factor out a pi times an h. And then we're going to have R2 squared minus R1 squared. And then R2 squared minus R1 squared can be factored using the difference of two squares. So we can say R2 plus R1 times R2 minus R1. And then I'm going to employ a little bit of a mathematical trick here, a mathematical manipulation. I'm going to divide this expression here by 2, and I'm going to multiply by 2 in front to cancel what I've done here. Now, why am I doing this? I'm going to explain. Let's go back to the diagram. So when you write R2 plus R1 divided by 2, you are taking the average between R1 and R2. Now, the average of R1 and R2 is the distance from the center of the cylinder to the center of the cylindrical wall, right? So let's remember that R1 was the distance from here to here. R2 is the distance all the way to the edge. So the average value is going to put you right in the middle there. So you can think of this as being the average radius. And we're going to call that R. So we have 2 pi h times R times, and then what is R2 minus R1? Well, again, R2 is the distance all the way out to the outer edge. R1 is the distance to the inner edge. So if I take this distance and I subtract that distance, I'm going to get the thickness of this cylindrical shell, and we're calling that delta R. So I can rewrite this as 2 pi times R times h times delta R. And this is the volume of a cylindrical shell. Now let's keep this in mind as we move forward to develop the process for finding volumes using this technique. Suppose we have some function y equals f of x, bounded by x equals a, x equals b, and the x-axis. And we're going to revolve that around the y-axis. When you do that, the resulting solid looks something like what you see here. So how do we find the volume of that solid? Well, let's zoom in a little bit. Here's our function. What I'm going to do is draw a representative rectangle here. And when that gets rotated around the y-axis, you can see that that rectangle forms a cylindrical shell. So what is the volume of that particular shell? Well, we know the volume formula for a shell is 2 pi times the radius times the height times delta R. So the radius is always from the axis of rotation, which in this case is the y-axis here, measured to the center of the rectangle. And that distance we're going to call xi bar. So xi bar is just the notation for the midpoint of this interval, okay? So again, if I'm at a particular x value here, the distance from here to here is that x value. So it's just the midpoint of that interval. So the volume is going to be 2 pi times xi bar times the height. Now, what's the height of your rectangle? Well, that's pretty simple. The height of the rectangle, of course, is just the function value at xi bar. So h is going to be f of xi bar. And then delta x is just the delta R that we're seeing right here in the formula, right? Because the delta R is the thickness right here. Well, we know that when you're talking about rectangles, the thickness of the rectangle is what we call delta x, okay? So when you have a function rotated around the y-axis from A to B, the volume of one of those rectangles is going to be 2 pi xi bar f of xi bar times delta x. But then to get the total volume, we're going to have to do this many times. So we take our interval, we divide it up into subintervals. Each one of these subintervals gives us a cylindrical shell when you rotate the rectangle around. And so the volume of all of these cylindrical shells are going to come from this formula. So all we're going to do is add up all of those little volumes, okay? So the idea is that the volume is going to be the sum, I equals 1 to n, of the volume of the ith shell. But the volume of the ith shell is what you see down here. So it's 2 pi xi bar f of xi bar times delta x. So what I'm trying to do right now is just develop the process for the formula. You don't necessarily have to think about it like this every time you do one of these problems, but it's always good to see how this stuff is derived at least once. And here is the final formula for finding the volume using cylindrical shells. So the volume is equal to the integral from a to b, 2 pi times x times f of x times dx. But again, I really want to emphasize that in this formula, the x that you see there is the radius, and the f of x that you see there is the height. Radius and height of what? The radius and height of the representative rectangle that you can draw that's being rotated around, producing that volume. All right, so let's go ahead and do the problem that we opened up this with. We want to find the volume of the solid obtained by rotating about the y-axis, the region bounded by y equals 2x squared minus x cubed, and y equals 0. So here is that region that we saw in the beginning. What I'm going to do is pick a representative rectangle here. Imagine that it is being rotated around the y-axis like this, and you can see that that forms a cylindrical shell. And now to do this problem, we have to figure out what is the radius and what is the height. But again, this one here is very simple. We can use this formula directly. The radius is just going to be x, because it's just the distance from the axis of rotation to the rectangle. And then the height, of course, is just going to be the function. So in this particular problem, the volume is going to be 2 pi multiplied by the integral from 0 to 2 of x multiplied by 2x squared minus x cubed dx. So you'll notice I pulled the 2 pi out, and that is because, 2 pi is a constant, and constants can be factored out of your integration. And I think you should factor it out. It makes the problem a little bit easier. Now I'm going to distribute x to both terms there. And now we'll take the antiderivative, which is going to be 2x to the fourth divided by 4, which simplifies to x to the fourth over 2, minus x to the fifth over 5 from 0 to 2. And so when you plug in 2, you get 16 over 2 minus 32 over 5. And then, of course, when you plug in 0, you get 0. So that is what that would look like there. And this is 2 pi multiplied by 8 minus 32 over 5. And that is 2 pi times 8 over 5. And this is 16 pi over 5. So not only is the problem not possible to do using the washer method, it's possible to do using the shell method, but it's also very easy to do using the shell method. So the shell method will make some problems that you did with the washer method much easier. In our next example, we wish to find the volume of the solid obtained by rotating about the y-axis, the region between y equals x and y equals x squared. So let's zoom in here a little bit. We have our function y equals x right here. Y equals x squared is right here. Notice that those two functions are bounded on 0 to 1. Okay, and this is because if you solve for where those functions meet, you would set them equal to each other. And then you'd set it equal to 0. And when you factor it, you would see that x equals 0 or 1. Okay, so we know that they intersect at 0 and they intersect at 1. And again, here are those functions. Now, this is the image of what you get when you rotate it around. Okay? So now we have to look at a representative shell. To do that, we take a vertical rectangle here. And then for that shell, we need the radius. How far is it away from the axis? Well, of course, that is just your x value. And then we need the height of that rectangle. And to get the height, it's very simple. We take the top function minus the bottom function. And the top function is x. The bottom function is x squared. So the height is going to be x minus x squared. So the volume will be 2 pi. We're going to integrate from 0 to 1. The radius is x, and the height is x minus x squared. So just like the previous problem here, when you go to do the integration, make sure you multiply this out first. And now we'll take the antiderivative of x squared, and we'll take the antiderivative of x cubed, evaluate it from 0 to 1. Now, when you evaluate from 0 to 1, you're just going to plug in 1, because when you plug in 0, you get 0. So we're going to have 1/3 minus 1/4, and this is 2 pi times 1/12, and this simplifies to pi over 6. In the next example, it says to use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals the square root of x. So now we are rotating this way. All right, so one thing that is really important when you're using the method of shells, and I always like to point this out to the students, is think about the 2 L's in the word shell. It should make you think of parallel, right? Because those L's are kind of like parallel to each other. Why am I saying this? Because when you draw your representative rectangle for the shell process, you always draw your rectangle parallel to the axis of rotation. So if we are revolving around the x-axis, we are going to draw our rectangle horizontally, because it needs to be parallel to that axis. Okay, this is what we did in the previous 2 examples as well. We drew them parallel to the axis of rotation. So once I do that, then it's just a matter of finding the radius. So again, the radius is the distance from here to here. And then the height is actually sideways now, right? The height of the rectangle, you have to think of that as a horizontal height, if you will. So what is the radius r? Well, it's the distance from here to here. But if you're on the y-axis, the distance from 0 to some y value is the y value. So we're going to have 2 pi. The radius will be y. And then what is the height of this rectangle? Well, again, you have to do it horizontally. To get the height, you take the right value minus the left value. Well, the right value is x equals 1. And the left value is x equals y squared. So the height is going to be the right value, which is 1, minus the left value, which is y squared. And yes, everything is with respect to y, because everything is reversed from the previous examples. And then we're going to integrate along the y-axis from 0 to 1. Now, once you get this set up, it's very similar to all the other problems that we've done so far. So we're going to multiply out the y. Then we are going to take the antiderivative. And finally, we'll plug in 1. And when you plug in 0, you get 0. And this is going to be 2 pi times 1/4, which simplifies to pi over 2. In our next example, it's a little bit different. Here we want to find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared and y equals 0 about the line x equals 2. So y equals x minus x squared is this parabola here. Y equals 0 is this horizontal line here. So you can see the region that we're looking for there. Now we can see that it intersects at 1, but if you were trying to figure that out, you would simply set x minus x squared equal to 0, and then solving for x, you would find that x is equal to 0 or 1, and that's how we know it crosses the x-axis at those two numbers. But from there, we are going to rotate it around x equals 2. X equals 2 is over here. This is the axis of rotation. Now you can see a nice picture of that in the next drawing. Here we have our region. It's being rotated around the line x equals 2. And when you rotate it around like that, your sample rectangle here is going to make this cylindrical shell. But here's the truth. Most of you, when you're doing these problems, you will not be making these kinds of drawings. Most students do not make these three-dimensional drawings. You certainly can if you want, but it's just not necessary. So, how do we find the volume here? Well, you need to remember that there are two things you need to know. You need to know the radius, and you need to know the height. So notice that your sample rectangle right here is drawn parallel to the axis of rotation. The average radius is the distance from here to here. Now, what is that distance? Well, this is an x value, and over here, this is x equals 2, right? We know that this is 2, and then this is some other random x value here. So what's the distance between these two numbers? Well, it's the right number minus the left number. So it is 2 minus x. That's the radius. And then the height is the height of this rectangle, and that doesn't change. That's just the function, x minus x squared. So your radius is a little bit different. It's not simply x anymore because we're not rotated around the y-axis like we had been. When you rotate it around a different line, you need to calculate the distance between that line of rotation and where your rectangle is. And to get that distance, you're simply going to be subtracting, in this case, the right value minus the left value. Now, once we have that, the volume is going to be 2 pi. We're going to have the integral from 0 to 1, because that's the limits of integration you see there. And then the radius is 2 minus x. And the height is x minus x squared. And then we just go ahead and do the integration. So we get 2 pi integral 0 to 1. We're going to multiply this out. That's going to give us 2x minus 2x squared minus x squared plus x cubed. And we'll simplify that a little bit before moving forward here. We have 2x minus 3x squared plus x cubed. Now we're ready to take the antiderivative. The antiderivative of 2x is x squared. The antiderivative of 3x squared is x cubed. And the antiderivative of x cubed is x to the 4th divided by 4. And then from here, we're going to plug in our limits. Now, a lot of our limits in this video have been 0 for the lower limit, which means you really didn't have to plug it in, because when you plug in 0, you get 0. Please don't make that assumption. Please make sure you check your lower limit, because a lot of times you're going to have to plug it in. But in this case, I only need to plug in 1. And when we plug in 1, we get 1 squared is 1, minus 1 cubed is 1, plus 1 to the 4th over 4 is 1/4. And so this is 2 pi times 1/4, which simplifies to pi over 2. Now, the last thing I want to do in this video lesson is talk to you a little bit about the difference between discs and washers versus cylindrical shells. So let's take a look at this particular example. Suppose I want to take the region bounded by the function y equals 2x, which is this line right here, and y equals x squared, which is the parabola here, and I want to rotate it around x equals -1. How would you do this if you were using discs and washers, and how would you do this if you were using cylindrical shells? So let's go ahead and talk about cylindrical shells first, since that's the method that we've been discussing so far. And then I'll come back and talk to you about how to do it using discs and washers. So first, let's take a look at this using cylindrical shells. To use cylindrical shells, we are first going to look at our region and draw a representative rectangle. Now, our axis of rotation is over here, so our rectangle needs to be parallel to that axis of rotation. And that really is the major key point here. We have to draw that rectangle parallel to the axis of rotation. All right, now from there, we need to compute two things. We need the radius, which is the distance from the axis of rotation to that parallel rectangle. So we'll call that r. And then we also need the height of the rectangle, which we will call h. Now, the radius is always the harder one to find. It's the one that will sometimes give students trouble. So where is that representative rectangle? Well, it's randomly drawn. I could have drawn it anywhere in here. So it corresponds to some value on the x-axis that I'm going to call x. So if I want to find the distance between this number on the x-axis, which is -1, and this number on the x-axis, which is x, to find the distance between two numbers horizontally, you take the right number minus the left number. And in this case, x minus -1 turns into x plus 1. Now, the height of the rectangle is simply the height that you see here. So to get that, you simply take the top function minus the bottom function. And so in this case, the height is going to be 2x minus x squared. And now that I have my radius and my height, I can go ahead and find the volume by using the formula for finding volume with cylindrical shells. Now, when you integrate, one key thing to point out here is that these two functions, 2x and x squared, they meet at the point 2, 4. Okay, if you set them equal to each other, you will get x equals 2 as the point where they meet over here. All right, so we're going to integrate from 0 to 2. And then we'll take the radius, which is x plus 1, and multiply it by the height, which is 2x minus x squared. And we'll go ahead and do all these calculations. And so, double check all of my work here. Make sure that you understand where all these are coming from, all these steps. And then we'll go ahead and combine like terms a little bit here. So let's see, we've got 2x squared minus x squared, that's x squared, minus x cubed plus 2x. So then we have 2 pi times, when you take the antiderivative, x cubed over 3 minus x to the 4th over 4 plus x squared. We're going from 0 to 2. We are going to plug in 2. 2 cubed over 3 is 8/3. 2 to the 4th over 4 is 16 over 4, and 2 squared is 4. And you don't have to worry about plugging in 0, because again, when you plug in 0, you get 0. So we have 2 pi, 8/3, and this is -4, and this is +4, so those cancel out. So we have 16 pi over 3. Now, we're going to do the same problem using washers. And we're going to see the profound difference between these two methods. And the key here is not to say one method is better than the other. You need to know both methods, because sometimes you'll have to use one method or the other depending on what the function looks like in any particular case. So now we are going to use disks and washers. And in this particular case, it's really going to just be washers. So when you're using disks and washers, it's a completely different method, and it starts right in the beginning. So remember, for shells, we drew our rectangle this way. When you're using disks and washers, you need to draw your rectangle perpendicular to the axis of rotation. So if I pick a random rectangle here, it's going to be drawn sideways, not vertically. That is the major key point of the difference between the two methods. So we draw that sample rectangle perpendicular to the axis of rotation. Again, the axis of rotation in this case is x equals -1. Now, the method for washers is a completely different method and has a completely different formula. So the formula is volume equals pi times the integral from a to b, big R squared minus little r squared. And then in this case, it will actually be dy, okay, because we are moving along the y-axis. Because these rectangles, when you draw them sideways, they start down here at the bottom and they run this way, right? And they run all the way up to the top. So these functions of r are going to be with respect to y. Now, because those are actually y values, we usually will put c and d on the limits of integration. So I am going to change that to c and d just to be consistent. But now we got to find big R and little r. So big R is the distance from the axis of rotation to the farther end of the rectangle. That's big R. Little r is the distance from the axis of rotation to the closer end of the rectangle. So now how do we get big R? Well, again, it's a sideways distance. It's a horizontal distance. To get a horizontal distance, you take the right function and you subtract the left function. But what is the right and left functions? Well, over here, this is just a vertical line, so that's x equals -1. But what is it here? Well, it's y equals x squared, but we have to solve for x because we're doing this with respect to y. So it's going to be x is equal to the square root of y. Okay, that's this one right here. And then the other one, which we're going to need in just a minute, the y equals 2x, that's the same as x is equal to y divided by 2. That's this function. So when I go to state big R and little r here, big R is going to be this value, which is the square root of y, minus this value, which is -1. And little r is this value, which is y divided by 2 minus -1, which of course gives us radical y plus 1 and y over 2 plus 1. So now we got to plug those into our volume formula. We have pi. We're going to integrate from 0 to 4 because on the y-axis, this point here is the point 2, 4, so they intersect at y equals 4, okay? And then we have big R, which is radical y plus 1, quantity squared, minus little r, which is y over 2 plus 1, quantity squared. And this is all integrated with respect to y. And I think it's pretty simple to see at this point that this method is a little bit more challenging than the shell method for this particular problem. Let's go ahead and work out this integral. So we have pi integral 0 to 4. When we multiply the square root of y plus 1 times the square root of y plus 1, you're going to get y plus 2 square root of y plus 1. Minus, and then when you multiply y over 2 plus 1 times y over 2 plus 1, this gives us y squared over 4 plus y over 2 plus y over 2 plus 1, and that simplifies to y squared over 4 plus y plus 1. All right, now let's simplify here. We have 1 here minus 1 here. Those cancel. We have a y here minus a y here. Those cancel. So it looks like all we have left is this right here, which is 2y to the 1/2 minus y squared over 4. Now let's take the antiderivative. So we have 2 times y to the 1/2 plus 1 is 3 over 2, divided by 3 over 2, minus y to the 2 plus 1 is 3 over 3, but then don't forget you already had a 4 down there. Okay, let's keep going with this. This becomes pi times 4/3 y to the 3/2 minus y cubed over 12. And now we are going to plug in the upper limit. We do not have to plug in the lower limit because when you plug in 0, you get 0. So let's just go ahead and plug in the upper limit, which is 4. We get pi times 4/3 times 4 to the 3/2 minus 4 cubed over 12. And this is pi times 4/3 times 4 to the 3/2 is 8. And then 4 cubed is 64 over 12. So we have pi times 32 over 3 minus, and if you divide the 4 out of this, 4 goes into 64 16 times, and 4 goes into 12 3 times. We will get pi times 16 over 3, which is 16 pi over 3. And if you rewind the video, we got the same answer using shells. So the two methods produce the same answer, but they are set up completely differently from each other. And you are not allowed to have a favorite because sometimes you can't do the problem one way or the other, and you need to know both methods. And that concludes this video lesson.